Friday. Okay, so this is the last lecture of the semester. As a topic, I wanted to discuss a fun problem that I came up with my kids a while back. I used this as a topic when I was giving the keynote address to the ATMIM, Association of Teachers of Mathematics in Massachusetts, I believe. What I want to do is talk about how to go from good questions to good mathematics. Most of you are probably not going to be looking at pages of equations in your future, but you will have some problems. And I want to teach you a little bit more on how to ask questions. Okay, so this was the 110th anniversary of the association. A lot of the themes was, where is math going? Where's math education going? What's the next 110 years going to look like? You may have been unfortunate enough to have had a class in algebra in junior high where you did 40 iterations of the quadratic formula. And you would get really good at solving the quadratic formula, but you might not have a sense of why you care about solving the quadratic formula. So today, I want to try to give you a sense of why we might care about some of these mathematical techniques. This is something that I think is not emphasized nearly enough. So one of the hardest skills to learn is how to think, how to attack a new problem. A lot of people freeze when they see something that doesn't match the mold of what they've seen before. And you basically need to be a little bit fearless and just go forward and just see where things go. Don't be afraid to try something. Don't be afraid to ask a question. So as I said, ask questions. Another thing is gather data. There's a lot of different ways to gather data. You could be pulling it from the web with some kind of script program, great skill to have. You could be numerically simulating. I strongly urge you to learn a computer science. You learn a program, learn how to write in R, Mathematica, C, Java, something, so that you can pull data and you can simulate. Now the question is how to motivate material. I like to play games, so we're going to use games today to motivate the mathematics. We are not expecting a fire alarm today, so I don't think I'm going to have to readjust my lecture, so there will be class participation today. So feel free to interrupt, make comments throughout. So these slides were from about a month ago. Kayla is now 4 plus a little bit, maybe 3 epsilon. Okay, so the M&M game. So last year when I was on sabbatical, Cameron asked me the following question. Daddy, if you're born on the same day as someone, will you die on the same day as someone? And I'm a mathematician. I never believe in saying no to a question. I always want to know, well, how can I answer it? So one possibility was to find 2 twins and kill one of them and show him, look, they didn't die on the same day. Now, well, mathematically, it's a perfectly acceptable solution. It is a proof. That proof, however, would have consequences. So I actually am in correspondence right now with somebody who's incarcerated who has submitted a problem for a journal I'm editing. And so I don't want to get to know him too well. So we will look for a different way to attack a problem like this. And so I created the M&M game. So everybody should have at least 2 M&Ms, if not more, and a coin. You may keep any M&Ms and grab more M&Ms on your way out, but you have to hand in the coins. Otherwise, I'm paying you. So here's how it works. Everybody starts off with the same number of M&Ms. In the interest of time, you all get 2. Cameron, Kayla, and I, we all got 5. And what happens is everybody gets a fair coin. The coin doesn't have to be fair. And at the same time, we all flip our coins. And if you get a head, you eat your M&M. And if you get a tail, you don't. And you keep doing this to see how long it will go until you're out of M&Ms. And so if both people end at the same time, it's a tie. Otherwise, somebody wins. So I want people to break up into groups of 2. So 2, 2, 2, 2, et cetera, et cetera. So break up, find a partner right now. Okay? If there's one person who's left over, I get to play. Okay? So following instructions. The instructions were to grab M&Ms and grab pennies. These are not hard instructions, guys. Okay? So is everybody paired up? Does everybody have a partner? Raise your hand if you don't have a partner. Congratulations, you're sitting right next to each other. Sadly, the game is easier with Cameron and Kayla. Okay, does everybody have a partner now? Everybody has a partner. Okay, I guess you don't have a partner? All right, I will play with you. It's my lucky day. All right, so now play. All I care about is whether or not you end in a tie, whether or not people end up dead at the same time. All right, ready? Let's go. If it lands on the floor, it lands on the floor. Head. All right.
So that means
head means you eat. Head. All right, so we end up in a tie. Good game. Okay. I like the well played, I heard. right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Once one person has died, it doesn't matter what you do. I just care, is it a tie or not a tie? So you have to keep going until, okay. All right. All right, has everybody finished? In each group where there was a tie, one person should raise their hand. I'll raise it. All right, so we have 1, 2, 3, 4 people with ties. I think it was around 14 groups. The correct answer should be around 20% of the groups should end up in a tie. And we'll see later today how to prove that it's 20%. So the numbers are actually not that bad and pretty consistent between section 1 and section 2. So what are some natural questions to ask about this game? Other than why are we playing it? What's a natural question to ask? What's something you might want to know about the evolution of the game? So you want to ask questions. You don't want to be the technician. You want to be the person who gives the technician commands of what to investigate. So what's something you might want to know about this game? Want to try?
The probability of heads versus tails.
So if the coin is fair, it should be 50-50. But if I give you a weighted coin, it might not be 50-50. So one question is, the input, is it a fair coin? But what's the question you might want to ask about the evolution of the game? I mean, what do I just want to know right now? So right now I was just asking, what's the probability of a tie with 2 M&Ms? So what's a natural generalization? Yeah, if we have 3 M&Ms or 4 M&Ms, what's the probability of a tie? Can you give me a formula for the probability of a tie as a function of the number of M&Ms? So you got to really get to the point where you ask questions. Don't just take things as given. Try to see what else could you study, what else could you ask. So in addition to just asking what's the probability of a tie with k M&Ms and 2 people, what else could you want to study? Changing the number of people. What if you have 3 people, 4 people? How does the probability of a tie change? Other questions you could ask is how long until one dies? One of my kids' friends' grandmothers writes children's stories, and she really likes the game, but she doesn't like this emphasis on death. And so she wants the game to be recast in a friendlier way, which Cameron and I refuse to do. So it's about death. How long until someone dies, okay? So, you can bias the coin, you can have more people. There's lots of different ways, but you want to get in the habit of asking questions. Don't just take things as given. It's good to ask open-ended questions and just see where things go. All right, so here's the probability of a tie in the M&M game, 2 players as a function of the number of M&Ms. So with 1 M&M, it's a 33% chance of a tie. With 2 M&Ms, 19%, and it keeps going, 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 going. This was the 110th anniversary of the association, so I carried out the calculation to 110 M&Ms. And of course, the natural question is, well, where will we be in 110 years? So where will we be with 220 M&Ms? So does anybody want to guess the probability of a tie with 220 M&Ms? Not so easy to look at this and see what the probability should be. Do you think the probability will go up or go down? Yeah. Probably will go down. So the question is, how quickly will it go down? And so when I look at a graph like this, I'm not quite sure exactly how steep that should be dropping off. So we need another way of looking at this data. Does anybody know another way of looking at data like this that might illuminate relationships? We've done this semester already. Logs. So when we looked at Kepler's third law, that period squared is proportional to semi-major axis cubed, by doing a log-log plot, things became a lot more interesting. So what we can do here is it's hard to predict what comes next. Logarithms are useful. If I do a log-log plot, so now this is the log of the probability of a tie, this is the log of the number of M&Ms. What does that look like? A line, right? I heard somebody say a straight line. I would say a straight line as well. I don't know what line is not straight, but I would also say straight line. And so I can draw the best fit line. So we've talked about the method of least squares. It's a wonderful way to calculate. And here's my best fit line. And so the probability of a tie, if I take its logarithm, this is the line I get, versus the log of the number of M&Ms. Or if I exponentiate, then I get the probability of a tie with k M&Ms is about 0.24 k to the 0.54. So let's see where we would be with 220 M&Ms. We would get 0.0127 as our prediction, but the actual answer is 0.0137. So we're off by a little bit. So the question is, how badly are we off? And do you see anything in the plot that makes you a little bit less surprised that we're off by a little bit? That maybe this is not the best straight fit line to use?
It seems like the first point is a little off.
I would say even more than just the first point. It's almost like I have this kind of curve coming in, and then in the limit it's becoming a line. So frequently it takes some time for the system to converge and settle down to the limiting behavior. This data over here is being given an undue influence in trying to find the best fit line, especially if you're using something like the method of least squares, where you square the error so you're off by a little bit. It has a great effect. And so a few points like here that are off, it's going to strongly move the line. It's going to move the line up here. It'll come down a little bit more over here. So a better way to attack the problem is not to use all the data we have. Throw out the data in the beginning. And so if we throw out the data in the beginning, now look at the best fit straight line. It's going essentially right through the center of all the dots. And if I extrapolate that, I get a slightly different formula than before. The numbers are a little bit different. And now if I try to predict what happens with 220 M&Ms, I get 0.01344 versus 0.01347. That's a pretty good fit. So this is a chance to plug what class? I would say not linear algebra here. I'd say statistics. You know, simulating, getting a sense of data, trying to interpolate and extrapolate what's coming. You could also say a little bit of linear algebra as well. We have a line here. So this is one where linear algebra is correct, but I would say statistics is also correct. It's the end of the semester. It's nice to plug what classes could you take next. Given some data, can I predict the future? I'm off by a very small amount here. I think there's something to this if I'm this close. And we're going to see in a little bit today how to actually find these values. All right, so I want to review one of my favorite moments of the semester, the basketball game. I think it's worth seeing again because there's so much good mathematics behind this. There's a really clever idea, and that clever idea is going to play a role here. Can people identify? Who are these players? And? Yes. So I'm old. These are the people I grew up watching basketball with, Celtics, Lakers. All right, so Bird and Magic are shooting first basket wins. Bird always gets a basket probability P. Magic always gets a basket probability Q. What's the probability Bird wins? We'll let X be the probability. And we want to compute this. So there's two ways to do this. One is we can break into cases. Bird wins on his first shot with probability P. To win on his second shot, he has to miss his first, Magic misses, and then Bird gets. To win on his third, Bird and Magic miss, then Bird hits. And in general, to win on his nth shot, Bird and Magic each miss n-1 times, and then Bird gets it on his nth shot. And so if we let R be the product of the probabilities of misses, then the probability that Bird wins is just going to be this infinite sum. So this is a nice way to see applications of sequences in series. We want to evaluate this series. So this is the geometric series, one of the most important series you'll encounter in mathematics. We want to figure out what does that equal. And so we showed that a nice way to attack this is through a memoryless process. And so if X is the probability that Bird wins, he can win on his first shot, or if he and Magic miss, what's the probability Bird wins from this point? So once Bird and Magic miss, what's the probability Bird wins? Not P. P is the probability that Bird gets his next shot. What's the probability that Bird wins the game after he and Magic both miss? It's going to be X. X is the probability Bird wins. Once they both miss, it's like we've just started the game all over. And so the probability that Bird wins is just going to be P plus 1 minus P, 1 minus Q times X. Well, we're writing R for 1 minus P, 1 minus Q. And so now we get the following simple formula. And what's nice about this is rather than having an infinite sum to analyze, we now have a finite ratio, just P divided by 1 minus R. One of the things we talked about during the semester is to tell when a series converges or diverges. We have lots of tests. If we want to approximate it, we can use the integral test. That's one of the nice benefits of knowing the integral test. It can approximate the value of a series. But what if I want to know the actual answer? If I have infinitely many terms to add, it's going to be very difficult to get the actual value. This is a much simpler formula. I would much rather take p and divide by 1 minus r than add infinitely many terms together. That's the power of this approach. And again, one of the nice things that you can do with this is you can use this to get the geometric series formula. And so the sum of all the r's has to be the same as this. After the dust settles, you get the geometric series formula. As long as r is less than 1, it's 1 over 1 minus r. All right. So what are the lessons we can draw from this? So the first is the power of perspective. To view this as a memoryless process, that once both of them miss, it's like we've reset the game, we've reset the analysis. This is an extremely important point in game theory. The other thing is, I hate doing algebra. This is a way to circumvent the algebra. Rather than dealing with an infinite series, which is hard to understand, I now have a simple ratio. The depth of a problem is not always what you would expect. Some problems are a lot easier if you can find the clever way of looking at them. If you take discrete math or probability, you'll see this all the time. The last is the importance of knowing more than just the minimum. You can start to make connections between different parts of mathematics. All right, so how does this apply to the M&M game? So the first thing I'm going to do is I'm going to show you the answer to the M&M game. This is the probability that if we have two players in k M&Ms with a fair coin, that we have a tie. It's this infinite sum where n choose r is n factorial over r factorial, n minus r factorial. It's the number of ways of choosing r from n when order doesn't matter. So again, most of you are probably not going to be flipping coins and eating M&Ms. I think you guys flip other things in your games. But I still want to talk about this formula. Why do I want to talk about this formula? When you look at this, can you try to isolate key facts and understand what's going on? So the first thing is, what do you think little n represents? We have a sum on little n, and it starts at k. So what do you think little n represents? So again, whenever you have, I'm sorry?
Number of M&Ms.
Well, I tell you, k is the number of M&Ms we have. I'm sorry? Not number of players. I tell you there's 2 players. So think back to the basketball problem. When we summed in the basketball problem, what did the n represent in that? The number of tries, how long it took for the game to end. So here, n is going to be how long it takes. It's going to be, this is going to be the probability of having a tie in exactly n tosses. You see things like 1/2 to the n minus 1, 1/2 to the n. How do you think you can view something like that? What do you think the 1/2 represents? Probability of a head or a tail. And if we're tossing it n times for each player, I should have a 1/2 to the n, 1/2 to the n. So again, most of you are probably not going to be playing M&M games in the future. I hope you will. It's marketed. But when you look at a formula like this, can you somehow glean what's going on? Can you isolate key features and say, what is this doing in the formula? What does n represent? What does this 1/2 to the n represent? That's what I want you to get out. This is one of the most important skills you can get out of math class. Can you look at something complicated and extract key points? Now, one of the things that was nice about the basketball game is there was a simple solution. There is a simple solution for this infinite sum. It turns out to be a special value of a hypergeometric function. Now, unfortunately, most of you have probably not seen hypergeometric functions. This is very advanced mathematics. It's way beyond what we're going to be able to do in 20 minutes. But there is a way to get a very nice one-line answer if you know the right one line to look at. So I want to try to explain where this formula comes from. So each turn, one of 4 events happens, and the 4 events are equally likely. So either both people eat an M&M, just Cam eats, just Kayla eats, or neither eats. And the probability of each one of these is 25%. So now, if I look at what's going on, imagine the game ends in a tie after n tosses. Well, the last toss for Cam must be a head, and the last toss for Kayla must be a head. Otherwise, they would have eaten all their M&Ms earlier. So that means in the previous n-1 tosses, in the first n-1 tosses, I have to have exactly k-1 heads for Cam. How many ways can I choose k-1 of n-1 tosses to be heads when order doesn't matter? This is the definition of a binomial coefficient. And then for each toss, I have a 50-50 chance of a head or tail. So it's just going to be 1/2 to the n-1. The last toss has to be a head. Similarly for Kayla. So this gives you the infinite sum. If you just look at this, it's not at all clear what this infinite sum evaluates to. But hopefully it's clear that it will evaluate to a finite number between 0 and 1. This is a well-defined game. There should be a probability of a tie. Can the probability of a tie be less than 1? Can it be greater than 1? No. Can it be less than 0? No. So this probability should be somewhere between 0 and 1. So without even knowing what this sum is, we have some sense. Now, why does the sum start with k? Why is the first term k? You know, I have two people, each have k M&Ms. This is the probability that I have both of them eating their last M&M on the nth toss.
You can't have less turns.
Right. You can't eat two M&Ms at the same time. That would be wrong. M&Ms must be savored. You eat them one at a time, right? I have to toss the coin at least k times. So the probability of a tie with fewer than, k tosses is going to be 0. All right. So we can use the lessons from the hoops game to understand this problem and convert it from an infinite sum to a finite sum. So the big lesson in the hoops game was this memoryless process idea. Can anybody see the analog of the memoryless process for the M&M game? So what was the memoryless process in the basketball? What allowed us to reset the game? What event? If both people miss. So what's the analog of both people missing in the M&M game?
Either both people eat the M&Ms or both people don't.
No. You're half right, half wrong.
Both people don't eat.
Both people don't eat. If both people eat, something's happened. So if neither person eats an M&M, it's sad, it can be a little traumatic, but it's like the game has just started again and that toss doesn't matter. So this memoryless idea comes into play. So the game is now finite. And now there's only 3 possibilities. And each possibility happens a third of the time. A third of the time, both eat an M&M. A third of the time, just Cam and Kayla looks on longingly. A third of the time, Kayla eats and Cameron looks on longingly. And now, I will let you do this calculation at home. This is the finite calculation. This is the probability of a tie after exactly n tosses. And again, the analysis is a little bit complicated here. I'm currently writing this up with some students, but it's a finite sum. Finite sums are much better than infinite sums. And with a little bit more work, you can even come up with a simple formula for this finite sum. All right, so let's interpret what's going on, and this is going to lead to other ways of attacking the problem. And again, my goal today is to just show you ways to attack math problems, as well as get some of the many M&Ms we have in our house out of the house. Okay? So let's let CK be hopefully obvious notation. C is the number of M&Ms Cam has. K is the number of M&Ms Kayla has. One of 3 things happens. They both eat an M&M, so I transition to the new stage of C minus 1, K minus 1 M&Ms. Just Cam eats an M&M, just Kayla eats an M&M. And so I can represent this graphically with a tree. So because there's so many things to draw, I'm going to just start off with each person having 4 M&Ms. And then one of 3 things happen. Just Kayla eats, both eat, just Cameron eats. And I just keep flowing down and seeing what happens. I start off with 100% probability up here, and I see how the probability flows all the way down into the last row. And what I care about is I need to end up here. This is the only way I can have a tie. Well, if I'm going to end up at a tie, I had to be at 1-1 a moment ago, and I had to flip 2 heads. So really, all I have to do is calculate what's the probability I land at 1-1, and then just multiply that by a third. Now what's complicated is there's so many different paths. To get to 1-1, I could go like this, flow over like this, flow like this, and come in like that. There's lots of different ways to move. To get here, it's very easy. There's only one way to get there, is go straight down. So I have to analyze all the different ways for the probability to flow. If you've ever seen Plinko on The Price is Right, it's kind of like that. I haven't done the calculation yet. It would be interesting to see how does the probability fall among all of these. I've only calculated what happens for 0, 0. So let's say we start off at the beginning where both people have 4 M&Ms. So I have 100% probability here. 1 moment later, a third of the time I land here, a third of the time I land here, a third of the time I land here. And I can just keep doing this and watch how the probability keeps falling. So if you want, I will post the slides. You can go through it at your leisure. And we see that 245 out of 729 times, we end up at 1-1. So then to get the probability of a tie, all I have to do is multiply that by a third. So the probability of a tie when they both start off with 4 M&Ms is about 11%. So this is one way to attack the problem, is this kind of graphical tree approach. All right. I want to show you some other ways. And so in the course, we're going to get to the Fibonacci numbers. So we define the Fibonacci numbers recursively. each number is equal to the sum of the two previous. I have to give you the first two Fibonacci numbers. Let's say the first two Fibonacci numbers will be f0 is 0, f1 is 1. I will post, or it's already posted, a very nice YouTube video I made with some students from OIT last summer. I want you to see this for several reasons. One, if you're interested in stuff like this is what you can do at Williams. It's phenomenal what the students can do. And two, it shows you some nice applications of generalizations of Fibonacci numbers in the real world. This is to the game of roulette. You know, the spinning the wheel with the reds and the whites, the reds, the blacks, and the greens. There's a wonderful strategy called double plus one, which many gullible people think will let them win in roulette. There's a fundamental flaw to that strategy. This video shows you how an analysis of like Fibonacci type numbers will prove that the strategy is bad. This is why I am not in Vegas, and this is why I'm here giving the lecture today. I gave you an extra credit problem to write down the first million Fibonacci numbers and all of their digits, or to just tell me how long it would take. If everybody in the two sections worked together, an unreasonable assumption, and if everybody knew all the Fibonacci numbers in their head and could just write down 10 digits a second without any calculation, another unreasonable assumption, it would take you 5.7 years to write down the first million numbers and all their digits. Okay, I wasn't too worried about anybody actually writing this or even getting a computer and printing it out. But to calculate how long it takes, one of the nice things is there's an explicit formula for the nth Fibonacci number. You don't have to calculate, you can just jump to wherever you want. And this gives us a great understanding of the sequence. And I will show you at the end of class today how to get that. What we can do is we can form a new sequence to understand the M&M game. For the most part in this class, we've only looked at sequences with one index, A0, A1, A2, A3. Once we looked at something that had three indices, when we looked at Conway's game of life, and we had each cell was either alive or dead at a given moment in time. There were three indices, the time, and then the x and y coordinates. So here I'm going to give you a sequence with two indices. XCK is the probability I end with a tie given that Cam starts with C M&Ms and Kayla starts with K M&Ms. And I want to calculate this. There are some values I know. If Cameron has a positive number of M&Ms and Kayla doesn't, there are issues, and I know that Cameron will definitely win. There will not be a tie. If Cam has no M&Ms and Kayla has a positive number of M&Ms, she wins. There will not be a tie. If they both start with 0 M&Ms, what's the probability of a tie? 1. And so I have this following recurrence formula. The probability of a tie when they have C and K M&Ms respectively is going to be 1/3 the probability when Cam has C minus 1, K minus 1, because a third of the time they both eat an M&M, plus a third of the time the probability when Cameron eats one and Kayla doesn't, plus a third of the time Cam doesn't eat and Kayla does. So I can write the probability of a tie with C, K M&Ms in terms of the other three possible states. And now I just have to solve this two-dimensional recurrence. Now, I got this two-dimensional recurrence by knowing that this was a memoryless process. Sounds a little bit funny to say, but what if I forgot it was memoryless? Okay? Could we still get to this recurrence relation if we forgot the memorylessness? I think, I don't know. Anyway, so what if we didn't see that? Could we still get here? Well, instead of having 3 possibilities, how many possibilities would we have? 4. And so we can write the following more natural recurrence. If I have CK for the number of M&Ms, then a quarter of the time I have CK, nobody ate, a quarter of the time both ate, a quarter of the time just Cam ate, a quarter of the time just Kayla ate. When you see something like this, it should be screaming at you to do a certain algebraic step. What should you do? I'm sorry?
Factor.
Okay, what do you mean by factor? I think you...
Take out the 1 over 4.
And put the 4 on this side? Yeah. I could do that. That's not going to fundamentally solve it. I will do something like that later, so hold on to that idea. But if you look at this, look at these terms, what do you want to do?
Take out the XCK.
On which side?
On the right side.
Yeah, take this XCK on the right side and move it over to the left. I shouldn't have XCK on both sides. Move it over to the left-hand side, and I have 3/4. Now I'm going to ask you what we should do. Now we take the 4 out, and when we clear the 4, then we divide by 3, and we get, oh, XCK is 1/3, there we go. And we recover the memoryless formula. And so there is a way to algebraically find this memorylessness, which I think is particularly nice. And so now we can solve this. So when we start off with 0, 0 M&Ms, it's clear that the probability of a tie is 1. When Cam has 1 M&M and Kayla has none, or vice versa, the probability of a tie is 0. And what I like about this is this reviews some of the stuff we've done in integration, this idea of symmetry, that sometimes the variables are occurring symmetrically. If I flip them, I still have the same thing going on. Now I can solve for what happens when they both have 1. If they both have 1, then 1/3 of the time they both eat, and that's going to be a draw. 1/3 of the time just Cameron eats, in which case Kayla wins. 1/3 of the time just Kayla eats and Cameron wins. So x11 is just going to be 1/3. x22 is a little bit more involved. To get x22, well, if Cam starts off with 2 M&Ms and Kayla 0, vice versa, the probability of a tie is 0. Now let's calculate x21. So Cam has 2, Kayla has 1. 1/3 of the time they both eat, in which case what happens? So if they both eat and we're at x10, what happens? Cameron wins. 1/3 of the time just Cameron eats, and now we have x11, which we know is 1/3. 1/3 of the time just Kayla eats, in which case Cam wins. And so we know this is 0, we know this is 0, we know this is 1/3, so the answer is 1/9. And by symmetry, this is the same as x12. We don't have to calculate x12, we know it from knowing x21. And now we can calculate x22. Again, we have our recurrence relation, and we can just keep repeating this process. Essentially, what we're doing is we're going through the tree. And this is just another way of writing that algebra. So in the interest of time, I'm not going to go through another one. There's something called Catalan numbers, which you can attack this problem with. What I'm going to do is I'm going to just write down the probabilities of ties with various numbers of M&Ms. If you look at the denominators, what seems apparent?
It's getting less and less likely than a tie.
It's getting less likely getting a tie. But what do you notice about the denominators?
They're all factors of 3.
They're all powers of 3. So let's clear denominators. It turns out you multiply by 3 to the 2k minus 1. That will clear all denominators. And you now get the numbers 1, 5, 33, 245, 19, 21, and so on. So you get a sequence of integer numbers. There is a wonderful website, and I've given talks on it, called the Online Encyclopedia of Integer Sequences. Yes, there is an encyclopedia of strings of integers. It's a wonderful site. You can put something into this, and it will tell you everything it knows, everything that people have inputted about the sequence. So if I put in my sequence here, it will give me the coefficients of, coming from the coefficients of like a Taylor series expansion of the following. It lists comments, it lists references, links, formulas. It has a lot of wonderful stuff. So, okay. All right, so OEIS. Okay, so can anybody figure out this sequence? What sequence is this?
Pi.
So these are the digits of pi. Right? Decimal digits of pi. It's not a particularly interesting sequence. There's not that much, well, but maybe it is. And so you start scrolling down, you see all the stuff that's known, all these different formulas to jump to the nth digit of pi. Absolutely incredible. It's also the decimal expansion of, oh my God, 104,348 divided by 33. And so the question is, why is this going on here? In 10 o'clock, they wanted to do the Fibonacci numbers. And so what I decided to do is not to put in the very beginning of the Fibonacci numbers, but to put in 3, 5, 8, 13, 21. And the very first hit, there were 8 of them, is, oh, so this is, I'll have to hit search again. Okay, there were 97 results found. The first one is the Fibonacci numbers. And what you'll notice is there's a lot that's known about the Fibonacci numbers. There's lots of formulas, lots of references, lots of links, more formulas. I'm still going examples, how to use it in Maple, Mathematica, programming, lots of different stuff. It's also the Economif numbers, if you reverse the Fibonacci. And so there's some formulas for that. One of my favorites as I was going down was consider a 3 by 3 by 3 Rubik's Cube, but you only allow certain moves. So the Online Encyclopedia of Integer Sequences is an extremely powerful site. It will show you connections you might not have thought of. It will also give you ideas of what to try to prove. You have this string, hey, have you thought of the following? And it's a way to make connections. You want to make connections between different parts of mathematics and science. Okay, so a couple of takeaways on what we've done up till now. So the first is always ask questions. I should be a little bit more specific. A good question is not, Professor Miller, why are you wearing this shirt? And I actually did get a question as to why I wore a specific shirt on my job interview at Williams. That was not a good question. Okay? good questions are somewhat open-ended that lead to good things. You know, what happens if I? Those are questions you want to try to ask. There are many ways to solve a problem. At the start of the semester, one of the first things we did was the proof of the Pythagorean formula. And I hope you had not seen the dimensional analysis that showed you a new way of looking at Pythagoras. So one of the important things is different methods of attack will lead to an emphasis of different structures of the problem, will help you understand different features. Experience is a very useful guide. You know, can you relate this to something you've seen before? To me, relating the M&M game to a basketball game with this memoryless really helped the attack, going from this infinite sum down to a finite sum. You need to look at the data the right way. You know, this is the power of the log. So frequently people understand the logarithm only as like this black box to just manipulate. You know, the logarithm exists for a reason. We can process data differently depending on how it's presented. And by doing these log-log transforms, it's often clearer what's going on. You also never know where the math is going to take you. You know, you can start off with a very simple problem. Conway is extremely good at something like this. One of my favorite examples of things he's done is the following. So try to figure out the next term in the sequence. So this is called the look and say sequence. Each line is reading the previous line out loud. I have 1, 1. I have 2 1s. I have 1, 2, and 1, 1. I have 1, 1, 1, 2, 2 1s. I have 3 1s, 2 2s, 1 1s. There's a lot of great stuff about this sequence that you would not expect. Conway is phenomenal. This is the Conway from the game of life at finding interesting, deep stuff from what would seem like trivialities. You never know where the math will take you. Okay. One of my favorite quotes is the following. If all you have is a hammer, pretty soon every problem looks like a nail. There's a lot of ways to look at this. One way is that people have their specialties. And if you're really good at doing technique X, whenever you get a problem, you want to apply technique X to it. The way I like to look at this is if you have a hammer, go to the land of the screwdriver. Go to the land where people don't have that technique, don't have that familiarity, and you have the chance of cleaning up. I strongly urge you to take classes outside of mathematics. You know, keep taking math, of course, but take classes in other fields, get other perspectives, see what questions they ask. I was a double geek math and physics. The physics stuff really helps me ask questions that a lot of my colleagues don't ask. And if you can ask different questions than your colleagues, if you have different techniques and tools than your colleagues, you have a chance of making progress. Otherwise, you are in a very crowded field of very well-trained people who all have the same tools, who are all using them to attack the same problem at the same time. This is very dangerous if you want to rise to the top. So what I want to briefly talk about now, we have about 2.5 minutes, is how to prove Benet's formula to jump to the nth Fibonacci number. And we're going to use one of my favorite techniques in mathematics, the generating function. So it's a nice way to talk a little bit about sequences and series. So I have my Fibonacci numbers, I have my Fibonacci recurrence, and I'm going to form this function g of x is the sum n goes from 1 to infinity of fn x to the n. Now the problem in doing this is, well, I don't know the Fibonacci numbers. That's the whole point. I'm trying to find them. How can I build this function g of x if I don't know the Fibonacci numbers? But I do know the Fibonacci numbers. I just don't know that I know the Fibonacci numbers because I have the recurrence relation. And once you have the recurrence relation in the first few values, then all the rest of the Fibonacci numbers are uniquely determined. So what I can do is I can start off, I can look at fn plus 1 x to the n plus 1. I use my Fibonacci relationship. I do some algebra. I shift my indices of summation, go through this slowly at home. And I realize this looks a lot like my generating function. Except this starts at 3, I was supposed to start at 1. So what I can do is, it's my generating function, but I have to subtract off f1 of x minus f2 of x because I don't have those terms. Over here, I have to subtract off f1 of x. This one is fine. And I can now use the bring it over method. I can put all the g of x's on the same side. We saw this earlier today. And I get g of x, after the dust settles, is x over 1 minus x squared. So I've told you in this class I will never give you an integral involving partial fractions. But partial fractions are extremely important. There is a reason you were taught them or should have been taught them. I can take this and I can factor the denominator and then I can expand things out with partial fractions. And now notice, I have something up in the numerator and I have something like 1 over 1 minus r. I can expand this out using a geometric series. I can expand this out using a geometric series. And when I expand this out, I'm going to get Benet's formula. I'll get the 1 plus root 5 over 2 to the n, and I'll get a negative 1 plus root 5 over 2 to the n. And there's Benet's formula. So this is the power of generating functions. I start off with just the fact that I have this recurrence relation, and I know the first two values, and I now have an explicit formula for the nth term of the Fibonacci's. So I hope today you were able to see some of the connections between disparate parts of mathematics. There's a lot of great stuff that's going on. The more math you know, the more connections you will see, the more tools you will have to attack these problems. Keep asking questions. Don't be afraid to start something and see where it goes. So thank you. I will see you on Friday, and I will be sending you an email as to exactly what the exam questions are going to look like. If anybody's interested in the Sable Lunch, I still have a few copies of this. I will be in my office. There'll be a lot of people coming from, I think, maybe a little bit after 2 to a little bit before 4 because of meetings. You can also try to get me at Mission Today at lunch if there's no Sabre people.